What do Euler's identity, often known as the greatest identity in all of mathematics, and quantum physics have in relation? You're about to find out. The constant E is coined to be the most natural constant because it shows up a lot in calculus problems regarding the rate of change. For instance, continuous interest requires the use of E. It shows up a lot in a power series. The function y equals e to the x is equal to its own derivative. Hence, y prime equals d e to the x over dx equals e to the x. Euler's identity is actually a special case of the general form, which is often known as Euler's formula, e to the I theta equals cos theta plus I sine theta. One night, when I was studying physics, a thought came into my mind, a possible link between simple harmonic motion, Euler's formula, and quantum physics. What is simple harmonic motion, you ask? I'll show you in just a moment. But first, let me introduce you to the wave function. This function tells you approximately where a particle would be at any moment in time in the quantum world, where x is the position and t is any moment in time. This is a very important function in quantum physics. I hypothesize that kx and omega t in this function are related to the mechanics of simple harmonic motion. And I'll show you my concept. Let's start! So let's imagine that a particle is moving around the origin in a circle with a radius of rotation of r meters and its angular velocity is omega radians per second. Well, then we can determine the x and y positions of the particle to be r cosine omega t and r sine omega t respectively. If we want to represent the position of this particle using a complex function, we can let x of t be the real part and y of t be the imaginary part. And so our position s of t can be written as x plus yi, which can be written as r times cosine omega t plus I sine omega t. Now, using Euler's formula, e to the I theta equals cos theta plus I sine theta, we can write this part as e to the I omega t. So therefore, this position function with respect to time would be r times e to the I omega t. Now, to get velocity, you take the rate of change of this function with respect to time once. And so you get r omega I times e to the I omega t. To get acceleration, you take the rate of change with respect to time twice. So you get negative omega squared r times e to the I omega t. Now, notice that multiplying any complex number by I rotates it on the complex plane by pi over 2 radians, or 90 degrees. And so we can see that the acceleration is omega I times the velocity, which means that the acceleration is perpendicular to the velocity. And since the velocity in this case is the tangential velocity of the particle, this acceleration is going to be the centripetal acceleration of the particle. So now we can move on to spring motion. Imagine that an object is tied to a spring with natural length L on a frictionless surface and is pulled by a distance of r. Once loose, it would begin simple harmonic motion, amplitude of r, and its period is 2 pi over omega. If we set the natural position of this object to be at x equals 0, well then we can determine the position of this object after t seconds to be r cosine omega t. To get acceleration, we take the rate of change of the position with respect to time twice, like I've said before. And so we get that the acceleration is negative r omega squared cosine omega t. Because the acceleration and the displacement are facing opposite directions, that means the acceleration must be proportional to the buoyant force of the spring, which carries the centripetal force. Since buoyant force is given by Fs equals Ks times delta x, and is also equal to mass times acceleration, which is negative r omega squared cosine omega t. And we can see that the delta x must be r cosine omega t, and the constant of buoyancy ks must be negative m omega squared. And because we know that the acceleration is the second derivative of the position with respect to time, we can get that the friction force is mx double prime, which is negative kx. By moving the negative kx to the left, we get mx double prime plus kx equals 0. We have derived Newton's buoyancy differential equation. The wave function appears to be a general case combining these two ideas. On a quantum level, the position, momentum, velocity, etc. of a particle is undetermined, so we need to keep track of the position and the time. If we look back to the wave function, we see that the omega t is related to natural frequency, which we've discussed in simple harmonic motion. The kx is related to the spring coefficient, which we talked about in the spring motion. I confess, the wave function I've been referencing isn't the only one. The wave equation has lots of different solutions, and the one I've been referencing is just one of them. The wave equation is a differential equation with many aspects other than the wave function, and the reasoning goes much deeper than what I've covered. It appears that sometimes equations in the quantum world may not be independent from normal scale physics, but rather a path that connects the two aspects. Einstein once put it that an imaginative mind carries much more potential than pure knowledge. So, I hope you guys enjoyed this episode, and I'll see you guys next time.